Hello friends, welcome again to my channel, and today we will discuss the design of flexible pavements based on the method given in IRC 37 2018. This code was first published in 1970, and after that it has gone several revisions, and in the latest edition both structural and functional performance of a flexible pavement are considered. Now this code is applicable to design a new flexible pavement or for reconstruction of damaged pavements for roads with a design traffic of 2 MSA or more. If design traffic is less than 2 MSA, then we should not use 37, but we should use IRC SP 72 2015. This code should not be used for design of overlay, for which either FWD method can be used, which is given in IRC 115, or Benkelman beam deflection study method can be used, which is given in IRC 81. The design philosophy in this code is the functional and structural performance of a pavement, and cracking of bituminous layer or cementitious material is considered as one of the design principle, and rutting of subgrade, granular layers and bituminous layers are the primary indicator of functional and structural performance of the pavement. So these are the performance criteria, and these parameters are explained in terms of stress, strain and deflections, which are calculated by using linear elastic layer theory. The pavement is modeled as multi-layer system. The bottommost layer is considered to be semi-infinite in both directions, horizontal and vertical, and all other upper layers are assumed to be infinite in the horizontal extent and finite in thickness. The input parameters are elastic modulus, Poisson ratio, and thickness of each layer. And IITPAVE software is used for the analysis of the pavement. Now, the critical parameters which are considered in the design of a flexible pavement are three. Vertical strain at top of subgrade, that is considered to be a causative factor for permanent deformation in subgrade, or you can say rutting. The horizontal tensile strain at the bottom of the bituminous bound layer, and that is the indication of fatigue cracking in bituminous layer, and horizontal tensile stress and strain at the bottom of the cement treated base. The subgrade rutting criteria given in IRC 37 is that if rutting is 20 mm or more, that is considered to be the failure condition, means the pavement has failed. And if you calculate the vertical strain, compressive strain at top of subgrade using IITPAVE, you can find out how many repetitions of standard axle load this pavement can take. Alternatively, you know the design traffic, and corresponding to this design traffic, what should be the permissible value of epsilon V, that is vertical compressive strain. And you design a pavement so that this strain is less than the allowable strain. This equation is used for 80% reliability, and this equation is given for 90% reliability. Now, reliability here means the 90% chances are that the pavement will last its design life. The fatigue criteria, which is considered in the design, is that if 20% of paved area is cracked, that is considered to be the failed condition. And here, this is the tensile strain at bottom of bituminous layer, and this is the resonant modulus of the bituminous mix used in the bottom bituminous layer. If you are putting two layers of bituminous mixes, then bottom layer should be considered. And again, there are two equations here for 80% reliability and for 90% reliability. We should use for NH and state highway and expressway, we use 90% reliability equation. Here C is a parameter which is given by this 10 to the power m, and m depends upon the mix condition, And that's the departure in this code from earlier code, that here we consider the mixed design parameter also while calculating the fatigue life of a pavement. This is the effective binder content, and VA is the air wires in the mix. So from this we calculate M, from M we calculate C, put the value of C here, and the tensile strain at bottom of bituminous layer, and MR value of the bituminous mix, and you can calculate how many cycles it can take or how many repetitions of standard axle load this pavement can take before the critical cracked area is 20% or more. For cement treated base, there are two considerations. One is based on tensile strain, another based on tensile stress. This equation is based on Australian experience, and here the RF is the reliability factor, which is 1 for expressway, national highway, state highway, and urban roads, and for other road also if the traffic is more than 10 MSA, and 2 for all other roads. N is the number of standard axle load repetition. E is elastic modulus of CTB material, and this epsilon T is tensile strain at bottom of the CTB layer. Now, another parameter here is based on the stress. Sigma T here is tensile stress at the bottom of CTB layer for given axle load class. So here we determine what is the fatigue life of CTB material for a particular load class I, and this MRUP is 28 days flexible strength of cementitious base, and the sigma T upon MRUP is called the stress ratio. From that you determine the cumulative fatigue damage CFD, summation of Ni upon NFI, and this value should be less than 1. So standard conditions which are taken for the design of flexible pavement are that material response model is considered to be linear elastic, the interface condition is fully bonded, number of wheels dual wheel, and wheel load is 20 kN on each single wheel, that is 2 wheels. Contact stress 0.56 MPa for tensile strain in bituminous layer, and vertical compressive strain on subgrade, and 0.8 MPa for cement treated base. And these three conditions are critical, as I explained to you earlier also. Now let us say you take a very conventional pavement where you have subgrade, granular subbase and base, and then you have bituminous layer. Now in this case there are only two critical conditions. One is the vertical strain on subgrade, top of subgrade, and tensile strain at the bottom of bituminous layer. Only these two conditions are critical. But when you have the CTSB, cement treated subbase, and cement treated base, then these three conditions are critical. The vertical strain on subgrade, the tensile stress and strain at the bottom of CTB layer, and tensile strain at bottom of bituminous layer. When you have a cross section where CTB and CTSB are used, but rather than providing the granular crack relief layer, you are providing the semi layer, then also the condition remains same. All three conditions are critical conditions. When you have emulsion or foam bitumen stabilized base, then in that case the critical conditions are only two: the vertical strain on subgrade and tensile strain at the bottom of bituminous layer. In case of CTSB, that is cement treated subbase, and above that if you provide normal conventional granular base of WMM, then only two conditions are critical: vertical strain at subgrade and tensile strain at bottom of bituminous layer. But when you are providing GSB, granular subbase, in the subbase course, and above that you provide CTB, and then a granular crack relief layer or SAMI, then all three conditions become the critical conditions. The design traffic is calculated using this equation, where A is initial traffic in the year of completion of construction, and that basically is calculated using this equation, where P is the number of commercial vehicles as per last count, R is the growth rate of the traffic, and X is the number of years between the last count and the year of completion. Now here VDF is the vehicle damage factor and D is the lane distribution factor. For understanding this vehicle damage factor, you can see my another video on how to calculate VDF, and link for this is given in the description box. Lane distribution factor depends upon the type of carriageway. If it is single carriageway, single lane road, it is 1. 2 lane single carriageway, it is 0.5, and 4 lane single carriageway, it is 0.4. And similarly for dual carriageway for divided highways, this lane distribution factor can be taken from this table. The vehicle damage factor is a multiplier to convert the given number of commercial vehicles having different axle configuration and different axle weights. I will not go into much details of this because this point I have already explained in one of my earlier videos, and you can refer that video for further details. A flexible pavement will have 3 functional layers above the subgrade, subbase, base, and bituminous layers. Now the subbase and base layers may be granular or may be cement rated or a combination of these two. Similarly, base layer can also be a foam bitumen or emulsion treated material, or it may be wrap material or combination of their combinations. When cement treated base is used, a crack relief layer is mandatory to provide. This can be either in the form of aggregate interlayer or it can be in the form of a SAMI layer. The top 500 millimeter of prepared foundation layer immediately below the pavement is called the subgrade. And the input parameter required for subgrade in IITPAVE is resident modulus, and resident modulus can be estimated from CBR value using these empirical equations given in the IRC code. When the subgrade is prepared using a material which is stronger than top 500 millimeter of embankment soil, then it is important to estimate effective CBR, which will reflect the contribution of both of these materials. And the maximum resident modulus of subgrade is limited to 100 MPa. Now, how do we determine effective CBR in case subgrade is provided on embankment and the soil used for embankment and subgrade are different? So first we calculate the maximum surface deflection from IITPAVE software, and for that input parameter will be single wheel load of 40,000 Newton and contact pressure of 0.56 MPa. It will be a 2-layer system where 500 millimeter thick subgrade layer laid over semi-infinite embankment layer. But in case of embankment layer also, we take only top 500 millimeter thickness. Means we consider CBR of the soil which is used in top 500 millimeter of embankment. Calculate elastic moduli of subgrade and embankment soil from the equation. Poisson ratio can be taken 0.35 for all layers, and we calculate the surface deflection. Now the surface deflection is used to calculate the resilient modulus. This is the resilient modulus of equivalent single layer. And if you know MRS value, you can find out what will be the CBR, effective CBR, using one of these two equations depending upon the value of CBR. In this equation, small p is a contact pressure which is taken 0.56 MPa. A is the radius of circular contact area, which is taken as 150.8 millimeter, and mu is the Poisson ratio. Now, let us take one example to demonstrate how effective CBR is calculated. An example is that CBR of the embankment material is 8% and CBR of the borrow soil, which is used to prepare subgrade, is 20%. So what is the effective CBR for the design? So for embankment soil, we determine what is the value of elastic modulus using this equation because it is more than 5%, and therefore we'll use 17.6 into CBR to the power 0.64, that is 66.6 MPa. And elastic modulus of borrow material is 119.7 MPa. Now this is the structure. You have two layers. The embankment has semi-infinite thickness, and above that you provide 500 millimeter thickness of subgrade soil, and these are E values. So with these values we calculate what is surface deflection using IITPAVE. Now let us go to the IITPAVE to illustrate this procedure. How do we find the surface deflection? This is IITPAVE software on my system. You just click it. First thing you have to do, you have to install Java. So this file JRE7U2 window i586 is to be clicked, and then it will install Java on your system. Once it is done, then you can start this IITPAVE start. So when you double click this software, here you say design of new pavement, and then so here you will say number of layers 2 and fill the values of elastic modulus. The first layer is your subgrade, therefore E value is 119.7. The Poisson ratio is 0.35. Thickness is 500 millimeter. The second layer E value is 66.6, that is your top embankment. Poisson ratio same 0.35. Wheel load is 40,000 and tire pressure is 0.56. We need only one analysis point, and that is the surface deflection below the load, and therefore depth will be 0 and radial distance will also be 0. So if you submit these data, it says submitted successfully, and then you run the program. So when you run the program, you can view the file here. This is the complete file. So what is required here? Displacement Z, that is surface deflection, 0.141 into 10 to the power 1, that means 1.41 millimeter. Now the surface deflection as calculated from IITPAVE is 1.41 millimeter, and this value when you put in this equation and you calculate MRS, that is 105.1 MPa. So this structure is now equivalent to this structure, where you have a semi-infinite layer of elastic modulus value 105.1 MPa. Now since the code says that the maximum value of E can be only 100 MPa, so you take 100 MPa in this equation and you find out what is the value of the CBR. So you take 100 MPa and put in this equation and calculate what is the value of CBR. CBR is 15.1%, and that is the design CBR. After subgrade, we prepare the subbase, and functions of subbase, as you all know, is to provide strong support for the compaction of granular base, to protect subgrade from overstressing, and it also serves as drainage and filter layers. When the subbase is provided in two layers, then the first layer will act as the drainage layer and the lower layer will act as the filter layer. In that case, each layer should be at least 100 millimeter thickness. If it is to be provided in a single layer, then minimum thickness of subbase should be 150 millimeter. The MR value of subbase is estimated using this equation, where H is the thickness of granular layer in millimeter and MR support is the resident modulus of subgrade soil. That is the base support provided by the subgrade. When we use cement treated subbase, then this minimum layer of CTSB should be 200 millimeter and elastic modulus can be estimated from the UCS test of the material, and 7 days UCS should be 1.5 to 3 MPa, and if it is not, for a weaker material it can also be 0.75 to 1.5 MA. E value is estimated using this equation, 1000 times UCS, and this equation gives you very high value of E. CTSB is likely to crack under the construction equipment itself, and therefore the code suggests that the modulus value of CTSB should be 400 to 600 MPa, and Poisson ratio for CTSB can be taken 0.25. After the subbase, we lay the base course, and it can be a granular base course or it can also be cement-treated base course. When we provide a granular base course, the minimum thickness is 150 millimeter. When both base and subbase are granular, then we estimate combined resident modulus for GSB plus granular base. And in this equation, this thickness becomes the total thickness of subbase and base course layer. And MR support will remain the modulus value of subgrade soil. When we use CTSB, then we can take MR value 350 megapascal if it is of crushed aggregate and 300 megapascal if it is natural gravel. In case of cement treated base, the minimum thickness requirement is 100 millimeter, and that can be estimated using IITPAVE. The minimum UCS of the material which is to be used as cement treated base should be 4.5 to 7 MPa, and E value is again taken as 1000 times UCS, but what the code suggests that the maximum value of E can be up to 5000 MPa. The maximum flexural strength required for fatigue analysis should be taken as 20% of UCS, subject to the following conditions: that for cementitious stabilized aggregate, it should not be more than 1.4 MPa, and for lime fly ash soil 1.05 MPa, and for soil cement 0.7 MPa. In case of pavement with CTB, a crack relief layer between bituminous layer and the cementitious base will delay the reflection of cracks from CTB layer to the bituminous layer, and therefore it is extremely important to provide crack relief layer between bituminous layer and cement treated base. Now this layer can be of dense graded aggregate of 100 millimeter thickness, or it can be a stress absorbing membrane interlayer which is elastomeric modified binder applied at the rate of 10 to 12 kg per 10 meter square, covered with 0.1 meter cube of 11.2 millimeter aggregates. But when this is provided, when semi is provided, then it is not considered as a structural layer. That means it is not included in the pavement composition. The wrap material with or without virgin aggregates treated with foam bitumen or bitumen emulsion can also be used as base material, and in that case minimum thickness will be 100 millimeter and modulus value will be 800 MPa. The Poisson ratio for this can be 0.35. Now bituminous layer is provided as per this table depending upon traffic condition. For 50 MSA or more, the mix type which is used in surface course can be stone matrix asphalt. It can be gap graded mix with rubberized bitumen or bituminous concrete, and corresponding binder course will be of DBM. So this table can be used as a guide to select the type of binder course and surface course. The resilient modulus of bituminous mixes will depend upon the temperature and type of binder and type of layer. And this table is given in IRC code to guide the designers to choose appropriate value of resident modulus. It should be determined, as far as possible, it should be determined in the laboratory when you design the mix. And if it is not possible, then we can take from this table also. Now, if the resident modulus value of the field mix is more than the maximum value indicated in this table, the value given in the table should be used. DBM may be laid either in one layer or in two layers. When you are putting DBM, that is the binder course, when we are putting DBM in a single layer, the target air wires for the mix design should be 3.5%. And we should find out the effective binder content to calculate value of M in fatigue equation. Field compaction should be to achieve 4.5% or low air wires. When it is laid in two layers, the bottom layer DBM will have 3% air wires, and that should be compacted at 4% air wires in the field. The procedure for pavement design as given in IRC code can be summarized in these 6 steps. Select a trial composition, and it should be based on the expected functional requirement of the layers. Then right proportioning of the mix ingredients and the design mix should be arrived at. As far as possible, the resident modulus should be determined in the laboratory, and if it is not possible, then we can take the value of MR from the table given in IRC code. Then we select the layer thicknesses. Trial thickness of various layers of the pavement will be guided by the experience of the designer as well as minimum thickness required for a layer. Structural analysis of the selected pavement structure by using IITPAVE, and through this software we calculate stress and strain at desired points at critical locations, and these stress and strain should be compared with allowable stress and strain by using performance models. And if allowable strain is more than the actual stress coming on the pavement, then the design is safe. Otherwise, we go for another iteration. And many times, few iterations will be required by changing the layer thickness or material type until the calculated strains are less than the allowable strain. Let us take one example. An example is like this. That design a bituminous pavement with granular base and subbase layer using the following input data. It's a conventional type of pavement. It's a 4-lane divided carriageway that will require 4-lane distribution factor. Initial traffic in the year of completion of construction 5000 CBPD, both directions combined. Traffic growth rate, value of R 0.06. Design life 20 years. Vehicle damage factor 5.2. Effective CBR of subgrade estimated 7%. And Marshall mix design is carried out for bottom bituminous layer for air wires of 3% and resulted effective bitumen content by volume of 11.5%. Now these are required to calculate value of C and M in fatigue equation. So the solution is like this. Lane distribution factor for a 4-lane divided highway is 0.75. Initial traffic in one direction will be 2500 CVPD. Vehicle damage factor is given as 5.2, and therefore we can calculate the cumulative number of standard axles to be catered for the design, and that is 131 MSA. CBR 7%, effective resistance modulus of subgrade for 7%, 17.6 into 7 to power 0.64, that is 62 MPa, and it is less than 100 MPa, that is the upper limit specified in the code, and therefore we will use 62 MPa as MR for subgrade. Now, since the design traffic is more than 50 MSA, therefore we will provide stone matrix asphalt or this GGRB, which is gap graded mix with rubberized bitumen or bituminous concrete, that is the first row of the table, with modified bituminous surface course and DBM layer with VG40 with viscosity more than 3600 poise at 60 degrees centigrade. Now let us assume this trial section that bituminous concrete is 40 millimeter, DBM 70 millimeter, and below that 80 millimeter binder course, that is the first layer, WMM 250 millimeter, and GSB 230 millimeter. And for these thicknesses we can calculate the properties. For subgrade we have found out 62 MPa and Poisson ratio is 0.35. For aggregate layer we will take combined thickness of 480 here. In this equation H is 480 and E support is 62. So you get E of granular material is 200 MPa and Poisson ratio is 0.35. For HMA, for BC and DBM, the value of 3000 MPa will be taken from the table. So this is the structure. This is the pavement structure. We have a subgrade where effective CBR is 7%, E value 62, mu value 0.35. Then we have an aggregate layer where combined thickness 480 millimeter, E value 200 and mu value is 0.35. And above that you have HMA with total thickness of 190 millimeter, E value 3000 MPa and mu value is 0.35. So for this composition, these are 4 critical locations. 1, that is below the wheel, 2 at the center of the axle, and 3 and 4. 1 and 2 are below the bituminous layer, and therefore here horizontal tensile strains are important. 3 and 4 are at subgrade level, and therefore compressive strain at subgrade level are important. And Q is the tire pressure, 0.56 MPa. This distance between the center of the tire is 310 millimeter, and therefore this 0.2 will be at 155 millimeter from the wheel load. So with these parameters, we can calculate the allowable strain at 90% reliability as per IRC 37. For fatigue model, this is the equation. Here C is a parameter which depends upon M, and M depends upon effective binder content and air wires. So if you put the value of air wires as 3% and VBE as 11.5%, you calculate value of M, and from M to a value of C, and put this value of C here. Now this equation modified with this equation, and if you put value of E as 3000 and NF as 131 MSA, that is our design traffic, you can calculate what is the allowable strain epsilon T, 150 micron. Similarly for rutting equation, if you put value of NR equal to design traffic at 131 million, you can calculate what is allowable compressive strain at the level of subgrade top, and that is 310 microns. Now these values, allowable strain should be more than the actual strain coming on the pavement. So we again go to IITPAVE to find out for the trial section which we assumed what are the strain values at critical locations. We again go to IITPAVE and design a new pavement section where you will see the number of layers. Number of layers is 3 and we need to put all the input data. For layer 1, the elastic modulus is 3000, Poisson ratio is 0.35 and thickness is 190 millimeter. For second layer, the elastic modulus is 200 MPa and Poisson ratio is 0.35 and layer thickness is 480. For third layer, which is subgrade, the elastic modulus is 62 and Poisson ratio is 0.35. The wheel load is 20,000 and tire pressure is 0.56. Now here we need the result at 4 points. The first point is below the bituminous layer, that is 190 millimeter, and below the wheel load the radial distance will be 0, and between the axle, at the midpoint of axle, the radial distance will be 155. Point number 3 will be top of subgrade, that is 670 millimeter, total thickness of the pavement above subgrade, and radial distance 0, that is below the wheel, and 670 at a radial distance of 155 millimeter. The wheel assembly is dual wheel and we submit these data. Once you submit these data, then you can run the program, and after that you can see the result. In this output, these values are critical. That is epsilon T, tensile strain at bottom of bituminous layer, and that is at the center of the axle. And similarly epsilon Z, that is compressive strain at top of subgrade soil, and that is also coming at 155 millimeter from the load. So the allowable strain is now 150 micron, which we calculated from fatigue equation, and actual strain is coming 145.8 micron. So the design is safe. Similarly, the vertical compressive strain on top of subgrade is 310, 301, and actual strain is 244, which is less than the allowable strain, and therefore design is safe. If these values are not safe, if any of these values is more than these values, then we have to redesign the pavement. We have to take another section by increasing the depth of the base, subbase or bituminous cores depending upon which strain is exceeding the limit. So friends, what we have learned in this session is the various provisions which are given in IS 37 for design of flexible pavement, minimum standards of thicknesses and performance parameters to be met in the design, and how to run the IIT software, and to complete procedure of designing flexible pavement. Thanks for watching. You can write your comments in the comment box, and please share my video and subscribe to the channel.